a special name for that structure, like the trivial? It's not
I think
trivial,
I'd say
right?
that, I just say billion group, right, because that's what it is, right? But they might say the ring with trivial multiplication, I would say, probably. Okay, so the last thing that we had, in our discussion was, we had this theorem that I'm so fond of, where if you have ring and there's some multiplicative set S and some ideal I, you can actually expand I to this larger ideal, which I'll call P sub I, hopefully kind of suggestively showing that it actually contains I, such that PI is prime, doesn't hit S in its maximum with respect to its property. So I'll briefly write I intersect S, it's empty when there exists PI containing I, such that PI prime PI intersect S is empty, and PI is maximum with respect to this property. That is to say that if we can find another ideal that strictly contains PI, it has to overlap that S. Now, this is actually kind of a good sort of, for me, a good sort of benchmark that a property that you have in commutative rings is a good property, right? A good definition is if it has this property, right? So really, it's not the prime that made it maximal. It was this property here. Your maximal with respect to this property, your prime ideal. This is actually, this shows up in commutative algebra. So for example, here's some other things that we'll see later. An ideal that is maximal with respect to not being finitely generated is prime. So if it's as big as possible, any ideal that contains it has to be finitely generated, it's prime. An ideal that is maximal with respect to being non-principal, that one is prime, right? So those are actually good properties, and we'll see that you can do a lot of stuff with this. Let me give you another kind of neat thing about this. Let S equal 1, which any commutative ring of identity has, and let I be the zero ideal, which any ring has, then there exists P sub 0 containing 0. Guess what? All ideals are big 0, such that P0 is prime and P0 is maximal with respect to excluding 1. What kind of ideals are maximal with respect to excluding 1? The maximal ideals. A truly maximal ideal, because it's as big as possible. Anything bigger than that, anything bigger than P0 has to have 1 in it, so it's a maximal ideal. So notice any commutative ring with 1 has a maximal ideal. So that statement follows from this observation here. And in fact, you can go further than that. Let I and R be proper, and let S be 1. notice that because of the fact that I is proper, it misses S. So there is a PI containing I, such that PI intersect one is empty and PI is maximal with respect to this property. Translation. If you have a proper ideal, it is contained in a maximal ideal, right? Which is the more general statement that we've already done as well. So it's always, I'm digging on this theorem, right? Because bam, bam, it got us a couple of earlier things just like that. Okay. So let me give you I'm gonna pass from this. I'm gonna show some applications to UFDs and PIDs, which are important classes of domains that you probably saw in 8510, probably saw it earlier than that as well. Let me remind you of a couple of definitions. An integral domain is said to be atomic So we say an integral domain is atomic if every non-zero, non-unit in R is a product of atoms. Remember, atoms and irreducibles are synonyms. So we say that an integral domain is atomic if, of course, zero isn't going to work for you and a unit isn't going to work for you. But if you have anything that's other than zero or unit, you can factor it in a terminating way. So you can write it down into a product of irreducibles. I've given you other extreme examples of things that are not atomic. Let me point out that fields are atomic vacuously because they have no non-zero non-units. Fields also are an example of something that have no irreducibles at all as well, which is kind of weird. We looked at, for example, Z bar, the ring of all algebraic integers, that had no irreducibles whatsoever. Here's a quick example of something kind of mixed. Let me explain what this is. This is a set polynomial. Where n. So it's a set of polynomials where I'm going to demand, well, all the coefficients are in, say, the rationals, but I'm going to demand that the constant term is an integer, right? And it's a little twist. So let me point out that if this were q plus xqx, then this domain's Euclidean. So in fact, it's principal ideal domain. This one is not even atomic. Anybody see an element that cannot be factored into irreducibles? Two. No, two can't. In fact, this domain is kind of exotic in the following sense. Sorry, yeah. This is actually called an AP domain. That's just for fun. It turns out that everything that can be factored into irreducibles can be factored into irreducibles uniquely. And if it's a product of primes, as a matter of fact. But there are some rogue elements in here that cannot be factored into irreducibles at all. And papers, right? X is one of them. And then, you know, I get all, my blood gets angered up here, but it's like, X, what are you talking about, right? That's degree one. Well, there's a Give me your favorite positive integer.
And.
That's too narrow.
Okay, well, 4, I don't know.
How about 4? Notice 1/4 x is a kosher element of this, it's in there, right? But 4 is not a unit in this, right? In the PID, if that were Q, if I allowed things from the field here, then this would be some silliness. It would just be units multiplying this. However, that 4 now is stuck. This isn't really a proof, but it turns out that x cannot be factored into irreducible, because if you factor x into irreducibles, then there will be a piece of it that has a monomial something times x, and then you can just pull more stuff out of it. So no, there's no terminating process to write this as a product of atoms.
What are the atomic elements of that ring?
I'm sorry, no?
What are the product of atoms in that ring?
So it turns out that everything that's got a factor of x in it can't be written as product of atoms.
Yeah.
So what does that leave you? That leaves you things that have constant term in z. And it turns out, so if you have, so suppose you have, I'll use your favorite integer, n plus. You can actually pull the n out of this. Now, this piece right here just factors down into its constituent primes from z, and there's no problem there. You can use a degree argument to show these are irreducible. And this will now factor in qx as a product of these polynomials. In fact, you can sort of regroup things if you like, where all the constant terms are 1, right? And since qx, I mean, this is fast and loose, I can go through something better later if you like, but this factorization here is essentially unique, right? So this is called an AP domain, which means atoms are prime. It turns out that everything that's a product of atoms is actually a product of primes. And anything that's a product of primes is unique. So here's what you got. You got the stuff that you can't factor at all into a finite number of atoms. And then everything that you can factors into a product of primes. So it's essentially unique. Okay.
So, another question, the irreducibles here are the polynomials with 1 as a constant term?
Well, they also have to be
Irreducible.
irreducible in QX. Yeah, like that, yeah. Right, so 1 plus x squared would be irreducible, 1 minus x squared would factor into smaller ones, right? So I'm gonna give you, what am I gonna do here? I'm gonna give you the old school definition of UFD. This is probably the one that you all saw. I'm gonna develop one that's more sophisticated, using these ideas with multiplicative sets. We say that the integral domain of R is a unique factorization domain. Well, let me see, an atomic integral domain. So I guess this is probably slightly improved from what you might have seen in the very first abstract algebra textbook. But R being an atomic integral domain, we say R is a UFD, unique factorization domain, if given the irreducible factorizations let's say alpha 1 up to alpha m equals beta 1 to beta n, where the alphas and the betas are all irreducible. Then Well, what do I have to satisfy? For you.
What do I-
Okay, the first thing is that they have to be the same length, right? The number of irreducible factorizations on the left should equal the number of irreducible factorizations on the right. But not only are the lengths right, but it's gotta be unique, right? So that means that they gotta pair off. So I'm gonna write something all fancy. Two, there exists sigma in Sn, the symmetric group, such that alpha I equals ui beta sigma I with ui a unit in R. What does this mean, really? This just means I can rearrange these so that the alpha i's and the beta i's pair off up to a unit factor, right? Like, for example, in the integers, I make no distinction between the factorizations, -2 times -2 times 3 and 2 times 2 times 3, right? So what it means to be, and it probably in your first abstract algebra class, it might have said, instead of saying atomic, a little bit more compact than that, it might say R is an integral domain and every element can be factored into irreducibles and then blah, blah, blah. So, some examples. UFDs. Any field. Always gotta start there, don't we? Right? Z. Right, that's kind of a prototype. Any field, polynomial ring. Right, and in fact, any field in any number of polynomial variables, I don't care if it's an uncountable number, is a UFD. Power series ring and a finite number of variables. This is a UFD. Z adjoined with a primitive pth root of unity. That's the primitive pth root of unity. For p less than, anybody know? For all p less than 23. And in fact, 23 and higher, it always fails. That's why Fermat's last theorem wasn't proved until the 1990s. But UFDs abound, and of course, actually, if you take any of these that are UFDs, then you can add infinitely many polynomial variables, and they'll still be a UFD. Okay, yes.
So the power series and infinite variables, it is known if it is UFD or not.
I can't even answer that question. Here's the problem. I don't know what power series ring and infinitely many variables are. There are at least 3 different definitions in the literature. So we'd have to first decide which one we're talking about, right? That's the problem. That area has, really, I don't think that area has been looked at very carefully. You would have to make that decision first. And I think that, yeah, it might end up in Arkham Asylum or something like that. So, proposition. So basically, I said this a little bit before, so let's kind of put this down on paper, if you will. let R be a domain. Well, that'll be our playground for this. I just want it to be an integral domain. And, okay, enough of that. If X and R can be expressed of course, as far as domain zeros primes, let's throw out zero. If a non-zero element of R can be expressed as a product of primes, then this representation is unique. And when I say unique, I mean up to permutation of factors and associates. By the way, let me make sure that I'm clear on this word here. Put this up here for you. So as a remark, if A and B and R, we say A and B are associates if A equals B for some in the unit of R. So basically, this is the more ringy theoretic way of saying they vary by sign. That's it, right? These are just what it means to be associates or unipoles. This is easily seen to be an equivalence relation. So this proposition right here says something very important. It says, if I can replace this word irreducible with prime, I don't need to worry about all this, right? Because this result says, hey, you know what? If you can if you got something that's a product of primes, you write it as a product of primes, baby, that's the only way to do it. That's it, right? There are no differences there. So let's prove this. So let's suppose that X can be written as a product of primes. We're going to go in by induction. So let me write this way. Let X equal P1 Pk, we induct on K. We induct on the number of prime factors. Notice that if K equals 1, then X equals P1, and it's pretty easy to see that that's unique, right? I mean, there's no other way to write P1 because remember, primes are irreducible, so you can't break that down. So now, we assume that this holds, let's say for all K between 1 and N, X, then, this representation unique. And I'll put the unique in quotes to sort of signify that, yes, you can rearrange things and change up to associates. So now let X Suppose that we have, x is n plus one prime. And now let's write, x another way. Suppose it's got this other irreducible factorization. Um, with each irreducible. I'm not even gonna assume prime, I'll assume the more general irreducible here. Well, what we have, of course, is P1, P2, Pn plus one is pi1, pi m. And so what does this mean? Well, this means and from this, what can we conclude?
Bn plus one divides one bi by I.
Right, so we can assume since Pn plus one is prime, we say Pn plus one divides m without loss of generality. Because it's prime, so it's got to divide one of those factors, so I'll just say it divides Pn. So by the way, what does this say about pi m?
Certain element.
Right, so pi m, so this means some are, that's what it means for Pn plus one to divide. Okay, so what does that mean about R though? R must be a unit, right? Because pi sub m was irreducible. And what have I done? I've taken the irreducible, I've broken it down into two pieces. I know this piece isn't a unit, so that has to be a unit. So again, what does that say about pi m plus one? I've just promoted it. It has gotten a battlefield promotion from irreducible to prime. So pi m is associated to Pn plus one. I'm sorry, that would be Pn plus one. And so what we have and so now we can cancel out the Pn plus one and go inductively. So x over Pn plus one, P1, Pn, which is U pi one, pi n plus one. But by induction, this is a product of n primes, right? And so that means, so by induction, got that wrong, didn't I? This should be pi n minus one, right? So by induction, M minus one is equal to N. And, each, pi I is associated to some piece. So of course, that means that M is equal to N plus one. These are all associated in the first N, and of course, the N plus ones come. So we're done. Find that. Is everybody clear on that? You seem very disturbed, not in a good way.
Never mind, I'm good now.
Are you okay?
Yes. I forgot we can cancel stuff in and go to main for a second.
Oh, well, right. That's right. Yeah, you can cancel. And of course, when I look at this fraction right here, this is of course just an element of the ring, right? Because Pn plus one by definition divides X, and in fact, its product is P1 up to Pn. Okay. Any other questions? Okay, so this leads us right into the following here. Let's see. Proposition. Let R be a domain and S the multiplicative set of elements that are products of units so sometimes I would say that this is the multiplicative subset generated by the set of units and set of primes. So it's basically all the units, right? Because you could have sort of no primes in that product, or it's a product of primes, right? So it's everything that I can write as a unit times a product of primes.
And
This-
when you say the multiplicative set, you mean the multiplicative of those set?
Yes. Then S. In fact, I don't even need to say, I could just say set here, then S is multiplicatively closed and saturated. Okay, so let's outline this real quick. Multiplicatively closed is fairly clear because typical elements S means that X is a form or so anything in the set can be written either as a unit or as a unit times a product of primes, not necessarily distinct in here. And notice it's multiplicatively closed because a unit times a unit's a unit, and a unit times one of these animals is a unit, and the product of two of these are longer strings. Everybody okay with it? On the other hand, now let's suppose for the saturated X, Y, and R, and X, Y is in S. Notice at first that the units are clearly saturated, aren't they? Because anything that divides a unit must be a unit. So if X, Y is a unit, then I'm done. X, Y are both units. If not, then we have X, Y is equal to P1, P2, PK for some collection of primes. So I'm gonna be sloppy. I'm gonna be sloppy to finish this off here, but I'm not above that. Here's the strategy of what we're gonna do. I'm going to, and in fact, this is probably a more elegant way to do this. Let me do this. Q1, Q2, where PI, QJ are prime. So I write this notation with a little bit of forethought, because here's what I'm gonna do. I'm gonna inductively divide both sides by every one of these primes. And what do I know when I divide? When I, notice P1 divides, this side of the equation, so it divides this. So P1 makes a choice. It either divides X or Y. It might divide both, but I can just pick, right? So suppose P1 divides X, and then suppose P2 divides X, and so forth and so on. I make these choices wisely. I'm going to define the PIs to divide X and the QIs to divide Y if applicable. And so notice that X1Y equals P2, PK, Q1, QT, X2Y equals P3, PK, Q1, QT, X2Y1 is P3, PK, Q2, QT. So I this, and essentially what we get eventually is, I guess we get X. Because eventually when you divide all these out, you only left with 1, 3. So XK, which equals P1 up to P, whoops. So XK and YT are units. You know, I've sort of reduced down to that first observation. And notice that X is equal to and Y, YT, Q1. And so S is saturated. Because both of these elements of the product are a unit times the product of atoms. Okay. Any questions on that? Okay, so I'm going to use this. I'm going to bootstrap sort of a better way to think about the UFD. So originally, sort of the beginning UFD was a characterization of UFD was what? It was atomic, and then when you have two factorizations, they have to have the same length. Well, two irreducible factorizations have to have the same length, and the factors have to be the same up to permutation in units. Here's a better way to think of it. I need domain here. An integral domain R is a UFD if and only if every non-zero, non-unit of R is a product of primes. Okay, let's see what we can figure out about this. So my blanket assumption is this is an integral domain. Yeah, the reason I did say that you have to bring that up is you can actually have, non-domains, which of course can't be any factorization domain because it's not a domain, that where every non-zero non-unit is a product of primes. And it doesn't have to be unique. In fact, I can go back, you remember the example I showed you with Z6 and 3, it's 3 times 3, which is 3 times 3 times 3, and any power of 3 is that. Well, 3 is a product of primes, and in fact, 3 is a prime itself, and that we're in zero divisors. But it can be written as 3 to the n for every n, so it's certainly not unique, is it? Right? Okay, so let's see why this works. Suppose you have a UFD. Well, what do I know? I'll need to show that every non-zero non-unit is a product of primes. So let X be a non-zero non-unit. Well, actually, you know what I'm gonna do? I claim every irreducible in R is prime. That's easy. I claim that every irreducible is prime. Right. Here's my proof. Let pi in R be irreducible, and suppose pi divides AB. Well, just take AB and factor it. Since R is a UFD, then A is equal to alpha 1 to alpha K. B is beta 1 up to beta M. These are irreducible factorizations. And pi divides AB. So pi gamma 1 gamma L is equal to alpha 1 alpha K beta 1 beta M. But because this is a UFD, pi is equal to alpha I, well, let me not say equal, pi is associated to alpha I for some beta K. Therefore, pi divides A or pi divides B. So the unique factorization forces that pi to be prime. So what do we have here? So if you have a UFD, we now know, since it's a UFD, every non-zero non-unit is a product of irreducibles uniquely, but we don't care because now we know it's a product of primes. On the other hand, the other direction follows immediately from what we've been doing. If X is a product of primes, this factorization is unique. And I guess if I was super careful, I would also point out that if X is a product of primes, then X is a product of irreducibles, and so R is atomic as well. Right, so I mean, that was one of the things that I kind of skipped over. Okay, I am going to leave you all with the last characterization of UFD that you should puzzle over the weekend. Fun. And we'll prove this next time. This is my favorite one. This is another kind of hint that some results in algebra is going to be strong because prime, irreducible, we've been talking about elements. This couches things in terms of ideals. Let R be an integral domain. The following are equivalent. Following conditions are equivalent. Number one, R is a UFD. Number two, every non-zero prime ideal has contains a non-zero prime element. This is astounding. This direction here is actually fairly easy. It is amazing that all you have to do is acknowledge that every prime ideal has some prime element within it. Bang, it's a UFD, right? This is slick because this is done in terms of the ideals. And it does depend on Zorn's lemma, or at least some previous things we've done. And we'll explore this next. Any questions? Yes.
The ring that we talked about, Z plus X, QX, that's not atomic, it's not, but it is, you said it's, AP.
It's AP.
So-
All atoms are prime.
Can you show me a non-zero prime ideal that contains, or that does not contain a principal prime?
The ideal generated by the ideal XQX.
Okay.
Yeah, that doesn't contain principal prime. It contains zero, but that's it, right? That's what the non-zero is a very important adjective here. Okay, other questions? Yes.
So a minute ago, you said it's important we say that R is an integral domain in the last theorem. You said R is a UFD. If you only have every non-zero non-unit of R is a product of primes, and you brought up Z joining square root of negative pi.
No, Z sub 6. I'm sorry. Yeah, I brought that ring that has zero divisors. Z sub 6. That's also a problem here because if you look at Z sub 6, you will find that every non-zero prime ideal contains a non-zero prime element, but Z sub 6 is obviously not a UFD because it's not even a domain. So you need domain. Okay, others. Let me remind you of the very easy and very fun, I think, math club talk today. So if you got some time, you might roll by. Otherwise, y'all have just a galactically good Labor Day weekend. We'll see you on Wednesday.